Hello and welcome to this GeoStudio Tech Talk on assessing dynamic stability using the Newmark deformation method. I'm Catherine Dompierre and I work with the GeoStudio engineering team here at Seequent. Today's webinar will be approximately 40 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields, including stability analyses, the movement of water, contaminants, air, and energy through the ground, and stress and deformation in soil and rock. The integrated GeoStudio software suite enables you to combine multiple analyses using different products into a single modeling project. In today's webinar, we will discuss how to combine Quake W and Slope W to evaluate slope stability during earthquakes. To introduce today's webinar topic, let's consider this slope. It is an idealized slope with simplified features, allowing for more efficient numerical analysis. Using a simple limit equilibrium stability analysis, the factor of safety is just over 1. The slope appears to be just stable given static conditions. But what if our site is in an area prone to earthquakes? Imagine an earthquake with 0.4 g of maximum acceleration and a duration of 10 seconds. Would this slope stay stable during this earthquake event? And how does the factor of safety vary throughout? During an earthquake event, several instances of upslope and downslope movements occur. You can anticipate that the factor of safety varies accordingly during the earthquake. Upslope displacements result in an increase in the factor of safety, while downslope displacements may lead to a safety decrease, and in the worst-case scenario, instability. The factor of safety remains more or less the same as the static factor of safety in the initial cycles. Subsequent movements do not impact the factor of safety negatively until about 2 seconds, where it falls below 1. The short moments of instability do not necessarily mean that the slope will fail, since the subsequent movement may quickly remedy the situation. However, it is still important to consider how much deformation occurred during the moments of instability. Let us review the methods allowing for this type of evaluation. The impact of an earthquake on slope stability can be evaluated by 3 different classes of methods. The simplest approach is the pseudostatic method, in which the earthquake loading is modeled with an equivalent static force. The second approach, listed here, the Newmark permanent deformation method, sometimes called the Newmark sliding block method, also represents a simplified approach for investigating the influence of earthquakes on stability. In this method, the mobilized shear force in the slope is calculated during an earthquake event. The dynamic resistance is then assumed to be equal to the static resistance to calculate the corresponding factor of safety. The third approach is to conduct a comprehensive dynamic stress analysis in order to capture the degradation of the material strengths during dynamic loading. Today's webinar will focus on the Newmark method, as it provides a simplified yet practical approach for considering dynamic stability. The Newmark method is a stress-based stability method. This means that the stability factor, equivalent to the factor of safety, is determined as the ratio of the resisting forces over the mobilized shear forces. The summation of these forces over all columns in a given slip surface yields the total resisting shear force and total mobilized shear force. When the total resisting shear force is divided by the total mobilized shear force, the result is the stability factor for that slip surface. Recall that the mobilized shear force of each column is determined by the shear stress along the base of the column, represented by tau in this equation, and its area, represented by beta. The Newmark method evaluates the dynamic stability factor and permanent deformations given key assumptions. The first is that the potential failure mass behaves like a rigid block. Secondly, this method assumes that the soil properties remain unchanged during shaking. As previously mentioned, this means that the shear resistance during an earthquake event is assumed to be the same as the shear resistance given static conditions. Thus, the numerator of the stressed base stability factor equation is the total resisting force under static conditions. This assumption limits the application of this method to only cases where no significant material softening occurs during shaking. While the resisting forces are assumed to be constant, the mobilized forces change based on the dynamic stresses computed during the earthquake event. Let us now review how quake W and slope W work together to conduct a Newmark deformation analysis. We start by completing a quake W dynamic stress analysis. Horizontal and vertical acceleration over time associated with the earthquake are defined in quake W. The corresponding stresses throughout the domain are computed using the equivalent linear model. Let us consider the results of the dynamic quake W analysis at this node in the domain. During shaking, the shear stress in this node changes significantly. Similarly, the X effective and Y effective stresses vary. Together, these contribute to changes in the mobilized shear stress over time, as demonstrated in this equation, where the mobilized shear stress is a function of the shear stress and stresses in X and Y. In the corresponding slope W Newmark deformation analysis, the computed mobilized shear stress is translated to the mobilized shear force at the base of each column along a slip surface. As previously noted, the sum of the mobilized shear forces at the base of each column in a slip surface are used to determine the stability factor during shaking. Ultimately, the change in mobilized shear forces over time due to the earthquake accelerations caused the stability factor to change over time. In addition to determining stability factor over time, the Newmark method is capable of estimating permanent displacements. Let us consider the theory behind this calculation. The average acceleration of a sliding mass during an earthquake can be calculated using Newton's second law of motion, where force is equal to mass multiplied by acceleration. When rewritten for the context of a sliding mass, the average acceleration is equal to the difference between the current and initial or static mobilized shear forces, divided by the summation of the slice weights, representing the total mass of the system. Average acceleration can be plotted against the stability factor, where the average acceleration associated with a stability factor of 1 is called the yield acceleration. In this case, the yield acceleration is 0.1 meters per second squared. This represents the minimum acceleration that will cause the sliding mass to move or displace. Thus, the average acceleration is necessary for determining permanent deformation of the system. When average acceleration is plotted over time, we can see all the times in the analysis where the average acceleration was above the yield acceleration value. The velocity of the sliding mass can be calculated over each time interval when the average acceleration exceeds the yield acceleration by integrating the average acceleration over time graph. We can then determine the cumulative permanent displacement of the sliding mass by integrating the area under the velocity versus time curve. The permanent deformation of the system over time is represented by the dark red points here. Now that we have reviewed how a Newmark analysis determines factor of safety, or stability factor, and deformation, let us move to GeoStudio to review how to set up the components of this type of analysis. For this demonstration, we will investigate the stability of a dam before and after an earthquake event. In GeoStudio, I will create a new project file by clicking on the New button. Here I will select the metric letter option for setting my units of computation and my printing page size. The Define Project dialog opens, where I will add the title, Newmark Analysis. The first step in setting up a numerical analysis is to create the geometry. To do so, I will first add a 2D geometry to my project file. I am going to use the geometry of the San Fernando Dam example file that is available on the GeoStudio website. I have already downloaded this file, so I will go back to GeoStudio and use the File Import functionality to bring in the 2D geometry from this project file. I can now see the regions in the dam cross-section. I wish to translate the imported geometry so the bottom of the domain is at an elevation of 0 meters. To do so, I will go to Modify Objects, draw a box around the entire domain, and enter -300 meters in the Y entry box under Move Selection By. When I press Move, the imported geometry is now positioned at the origin. Before continuing, let me save my project file. And go to Define Scale to modify the reference scale to 1 to 900 so the displayed numbers are a more appropriate size. The next step in the numerical modeling procedure is to define the physics to be applied to the domain. This is done by adding analyses to the project tree. Back in the Define Project dialog, I will add a QuakeW initial static type of analysis. I will name this analysis 1 Initial Stress State. The initial pore water pressures for this analysis will come from a piezometric surface, which we will define in a later step. I will then add a QuakeW equivalent linear dynamic type of analysis as a child of the original static analysis and rename this to Earthquake Shaking. Both the initial stresses and pore water pressures will come from the parent analysis. I will also ensure that the cumulative values from previous analyses are excluded from the dynamic analysis. Under the Time tab, I will use the option to define the time steps from the horizontal earthquake record. To define the horizontal earthquake record, I can copy and paste data from a spreadsheet or from another GeoStudio file. In this case, I will use the horizontal records from the San Fernando Dam example file by opening the Earthquake Records dialog in this file, right-clicking in the data box, choosing Select All, and pressing Ctrl-C to copy the data. Back in my project file, I will press the Paste Points button to paste the earthquake data. Note that the peak acceleration of this earthquake record is 0.6. However, you can choose to scale it up or down using the modifiers portion of the Define Earthquake Records window. For example, if I want to test the effect of a similar motion but with an increased intensity, I could input a modified peak acceleration of 0.75. This means that a scale factor of 0.75 divided by 0.6 would be applied to all data points. You can also use the modifiers portion of the window to change the overall duration of the earthquake event. I will ensure the baseline correction option is selected. There is no guarantee that acceleration data leads to zero displacement at the end of the earthquake, which means some permanent displacement would remain. The baseline correction option modifies the acceleration data so that the displacement at the end of the earthquake is zero, ultimately bringing the domain back to the position it started at. Now let me add a description of these records, and then press View to see the scaled time history. We now have both of our QuakeW analyses added to the project tree. Ultimately, we want to evaluate stability at this site. First, let us add a SlopeW analysis as a child of the initial static analysis to evaluate the stability under static conditions. This will be a QuakeW stress type of stability analysis. I will rename the analysis 1A Initial Stability. On the Slip Surface tab, I will change the direction of movement from right to left and ensure the Entry and Exit Slip Surface Definition method is selected. Under the Convergence tab, I will change the minimum slip surface depth to 1 meter to avoid the evaluation of very shallow slip surfaces. Now it's time to add a Newmark deformation type of slope W analysis as a child of the earthquake shaking analysis. I will rename this analysis 2A Newmark deformation. Under the Slip Surface tab, I will select right to left for the direction of movement and specify that only the critical slip surface from the static stability analysis is evaluated by selecting the Other GeoStudio Analysis option and choosing the 1A Initial Stability Analysis. Note that we can define the slip surfaces using the same options as other stability analyses. However, in this case, I have chosen to only investigate the slip surface that had the lowest static resistance to decrease solve time. Now that the analyses are established, I will close the Define Project dialog. The next step in the numerical modeling methodology is to define the material properties. In the Define Materials dialog, I will add a new material and name it alluvium. I will use the equivalent linear material model to define its properties. I will assign a unit weight of 20 kilonewtons per cubic meter and a Poisson's ratio of 0.4. To define the G reduction function, I will press on the ellipses button, add a new function named alluvium, and select the spline data point function type. I will use the estimate option to generate the G reduction function using a confining stress of 100 kPa and a plasticity index of 5. To better view the function, I will select the Xlog option. Back in the main Define Materials dialog, I will select the estimated G function in the corresponding drop-down menu. I will also create a function for the damping ratio by switching to the function option, pressing the ellipses button, and adding a new function named alluvium. Again, I will select the spline data point function type and estimate the function using the confining stress of 100 kPa and plasticity index of 5. I will ensure this function is selected for the damping ratio in the main Define Materials dialog. The final function that I will create is for the maximum shear modulus, or Gmax. After switching to the function option and pressing the ellipses button, I will add a new function also called alluvium, and select the spline data point function type. I will estimate the function using the granular soil estimation method, with the default values based on a dense gravel. After pressing OK, the function appears in the window. I will ensure this function is selected under Gmax in the main Materials Definition dialog. The next material that we will add is called hydraulic fill. As with the alluvium, I will use the equivalent linear material model to define its properties. I will assign a unit weight of 18 kilonewtons per cubic meter and a Poisson's ratio of 0.4. I will define the G reduction function using the same method that I followed for the alluvium material. I will create a new function named hydraulic fill using the spline data point function type. To estimate the G reduction function, I will use a confining stress of 100 kPa and a plasticity index of 15. Back in the main Define Materials dialog, I will select the estimated G function for the hydraulic fill. I will also create a function for the damping ratio. I will name the new function hydraulic fill. Select the spline data point function type and estimate the function using the confining stress of 100 kPa and plasticity index of 15. I will ensure this function is selected for the damping ratio in the main Define Materials dialog. For the maximum shear modulus, I will create a function called hydraulic fill. Using the spline data point function type. The function will be estimated using the granular soil estimation method, with the default values based on a medium dense sands. I will ensure the hydraulic fill function is selected under Gmax in the main materials definition dialog. The final material I will add to this project will represent the dam shell, using the equivalent linear material model. I will specify a unit weight of 18 kilonewtons per cubic meter and a Poisson's ratio of 0.3. I will create the G reduction function using the same method as the previous two materials. In the estimation dialog, I will enter a confining stress of 100 kPa and leave the plasticity index as 10. In the Define G reduction functions dialog, I can select all three functions to compare them. Back in the main Define Materials dialog, I will select the shell G reduction function. The damping ratio function will also be defined in the same way. In the estimation dialog, the confining stress will be set to 100 kPa with a plasticity index of 10. The maximum shear modulus function will be named shell. And will be estimated with the granular soil method and the dense gravel material default values. Now that the dynamic material properties are defined, we need to consider the properties of the alluvium, hydraulic fill, and dam shell for the stability analyses. While the Define Materials dialog is open, I will select one of the stability analyses in the project tree. For the alluvium, I will use the Moore-Coulomb material model. The unit weight of 20 kilonewtons per cubic meter, defined for the dynamic material properties, has already been added to the material definition dialog. I will enter a cohesion of 5 kPa and a friction angle of 34 degrees. For the hydraulic fill, I will also use the Moore-Coulomb material model, with a cohesion of 15 kPa and a friction angle of 32 degrees. Finally, for the shell, I will use the Moore-Coulomb material model with a cohesion of 0 and a friction angle of 36 degrees. My material definition is complete, so I can close the Define Materials dialog and apply the materials to the domain. In the initial stress state analysis, I will press the Draw Materials icon and will select the Apply to Multiple Analyses option. I will ensure that all analyses are selected, and then will apply the alluvium material to the thin bottom layer in the model domain. I will then apply the hydraulic fill to the 3 middle regions for all analyses. Finally, I will apply the shell material to all remaining regions in the cross-section. I've now finished defining and applying the materials, so I will move on to setting up the initial and boundary conditions. For the initial stress state analysis, we specified that the initial pore water pressure conditions would be defined using a piezometric line. I will go to Define Piezometric Surfaces and add a new surface. I will enter the following coordinates representing the piezometric surface into the points portion of the dialog: 0, 33, 173, 33, 312, 5, and 350, 5. Under the Properties tab, I will change the maximum suction to 5 kPa since the materials at this site are all granular. Now that the initial pore water pressure conditions are defined, let us move on to defining the boundary conditions for the dynamic analyses. I will select the Draw Boundary Conditions icon and then press Define to review the predefined options. We already have boundary conditions for zero rotation, fixed X, fixed Y, and fixed XY. The only other boundary condition we will need is one to represent the dam reservoir. I will add a new stress strain boundary condition and name it Reservoir Pressure. I will select the hydrostatic pressure type of boundary condition and set it to be a constant value of 33 meters. I can now draw the boundary conditions onto the domain. In the initial stress analysis, I will apply the reservoir pressure to the lines where the reservoir is acting on the domain. I will apply the fixed X boundary condition to the vertical edges of the alluvium material, and the fixed XY boundary condition along the bottom of the domain. In the earthquake shaking analysis, I will apply the fixed Y boundary condition to the vertical edges of the alluvium and the fixed XY boundary to the bottom of the domain. The last detail that is required for the two QuakeW analyses is to set the mesh properties. I will open the Draw Mesh Properties dialog and change the global element size to 2 meters. I will also add secondary nodes to all elements by selecting the entire domain, choosing selected regions from the drop-down list, and under the Elements tab, select Apply Secondary Nodes. Finally, in the earthquake shaking analysis, I will add 2 history points. History points are locations at which the complete motion history can be saved. Thus, this feature can be used when you wish to view all computed acceleration, velocity, and displacement values at a point for all steps, regardless of whether or not the step has been saved. I will use the Draw History Point command to add 1 history point on the upstream crest of the dam and 1 at the bottom in the center. The last component that we must define are the slip surfaces for the slope W analyses. Recall that we chose the entry-exit method to define the slip surfaces for the initial stability analysis. In this analysis, I will select the Draw Entry and Exit Slip Surface command and will draw the exit range at the upstream toe of the dam and the entry range at the crest of the dam. I will change the number of increments to 12 for both ranges. The Newmark deformation analysis only assesses the factor of safety associated with the critical slip surface from the initial stability analysis, so we do not need to define any slip surfaces for this second slope W analysis. We are now ready to solve the analyses, so I will ensure all analyses are selected and press Start in the Solve Manager window. Let us start interrogating the model results by considering the initial stress state analysis. In the Draw Contours dialog, I will add a new contour to represent effective Y stress. After applying this contour to the domain, I would say that these contours look correct, since the unit weight of the shell and the fill are the same, and the contours match the geometry with no stress concentrations or abnormalities. To view the pore water pressure results, I will go to Draw Isosurfaces, add a new isosurface, change the category to Pore Pressure, and make sure this isosurface is turned on. The isosurface representing a pore water pressure of 0 matches the initial piezometric surface I defined, as is expected. In the Draw Graph dialog, I will add a new graph and name it 1 Y Effective Stress Profile. I will set the locations using the Select Custom Location option, and then will hold the Shift key while drawing a line through the center of the dam. Back in the Draw Graph dialog, I will select Effective Stresses, Y Effective Stress, versus Y in the drop-down menus. To rotate the graph so Y is plotted on the Y-axis, right-click on the plot, go to Options, and select Rotate 90 degrees. The gradient of the Y effective stress profile changes at an elevation of 33 meters, which corresponds to the position of the water table. I will clone this graph, name it 2 Pore Water Pressure Profile, and change the parameters to Pore Pressure, Water Pressure. The constant pore water pressure above the water table corresponds to the maximum suction of 5 kPa that we defined when setting up the piezometric surface. We can select both graphs to compare their shapes. We will now examine the stability of the upper slope under static conditions. The critical factor of safety is substantially greater than 1, so we have a stable slope. I can draw all the slip surfaces at once by going to the Draw Slip Surface Color Map command and selecting Show All. The slip surface colors represent the corresponding factor of safety. This visualization tool allows us to observe patterns of failure on the domain. Let us now look at the earthquake shaking analysis. The deformed mesh can be visualized on the domain, as shown here. To turn on the deformed mesh, you can go to Draw Vectors, select the XY displacement option, and specify that the vectors are drawn as a deformed mesh instead of vector arrows. I can click through the analysis steps to see the deformed mesh change over time, along with the Y effective stress contours, which are still visible on the domain. I will now open the Draw Graph dialog to investigate the dynamic stress results in greater detail. The 2 graphs we created in the initial static stress analysis are available here. Let us create a new graph titled 3 Acceleration at Base. Using the History Point graph type. In the Set Locations dialog, I will select the history point at the bottom of the domain. Back in the Draw Graph dialog, I will select Accelerations, X acceleration versus time in the parameter drop-down menus. I will right-click on the plot, go to Options, and turn off the symbols so it is easier to see the acceleration data. If we were to compare this acceleration plot with the inputted earthquake record, we would find that they are similar given the position of the history point we selected, which is at the bottom of the domain. Recall that the points along the bottom of the domain are fixed in both the X and Y directions, meaning that we would expect that the acceleration results at these nodes match the applied accelerations. Let me clone this analysis. Change the name to 4 Acceleration at Crest. And use the top history point instead. We can now select both the 3rd and 4th graphs to compare the acceleration at the bottom and top of the domain during the earthquake event. It is evident that these points experience different motions during the dynamic analysis. Another method for interrogating dynamic stress results is to consider the variation in shear stress along a profile. To do so, we can clone our first graph, rename it 5 shear stress profile, and change the parameters to total stresses, XY shear stress. We could plot all the time steps, or select a few to observe the changes in shear stress with depth compared to the initial time step. Recall that it is these changes in stress that may trigger slope instability, which we will now review in the Newmark deformation analysis. In the slip surfaces window, there is only one slip surface listed. This is because we chose to only investigate the stability results of the slip surface with the lowest factor of safety from the initial static stability analysis. You will notice that the factor of safety, deformation, velocity, average acceleration, and yield acceleration are listed in the slip surface window. When I click through the various steps in the Steps window, the corresponding values change in the slip surfaces window. However, it is easier to observe these changes as plots in the Draw Graph dialog. Let us first consider the factor of safety versus time graph. Some of the factor of safety results appear to be quite large. We are not concerned with these values, but rather the ones right around a factor of safety of 1. I will change the y-axis range to display a factor of safety from 0 to 5. We can now see that there are 3 points during the earthquake event where the computed factor of safety is below 1. Recall that the average acceleration associated with a factor of safety of 1 is called the yield acceleration. In the factor of safety versus average acceleration plot, if I change the vertical axis range again, I can see that the yield acceleration is around 0.18 meters per second squared, which is also provided in the slip surfaces window. The yield acceleration is the acceleration causing moments of instability, which can lead to permanent deformation. In the average acceleration versus time plot, I can identify the same 3 moments where the average acceleration is above the yield acceleration. If I click on the velocity versus time graph, the 3 moments of instability result in movement of the sliding mass, represented by the non-zero velocity values. Velocity over time is used to compute the accumulated deformation of the sliding mass, which is illustrated in the deformation versus time plot. The cumulative deformation computed in this Newmark analysis is 0.009 meters or 9 millimeters. This concludes our review of assessing dynamic slope stability with the Newmark deformation method in GeoStudio, using both Slope W and Quake W. As we have learned today, the Newmark permanent deformation method can be used to evaluate dynamic stability and permanent displacement of slopes during an earthquake. This method assumes that the strength of the material remains the same as the static strength throughout shaking. In cases where significant degradation of material strength is expected due to the excess pore water pressures or strain softening of the material, this method may lead to an overestimation of the factor of safety or unconservative results. Resources related to this webinar are available online. A Slope W Fundamentals course is available through the Seequent Learning portal. The only thing required to take this course is a Seequent ID, which can be created for free. 2 example files on the Newmark method are also available on the GeoStudio webpage. To learn more about GeoStudio in general, there are many tutorial videos, example files, product manuals, and past webinars available on the GeoStudio website. We have now reached the end of this webinar. I hope you have appreciated this introduction to the Newmark permanent deformation method. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.